video is about capacitors as components, physical objects. It corresponds roughly to sections 10.1.1 and 10.1.2 of the Applied Analog Electronics textbook. Now, in this class, we generally use just ceramic capacitors, but they're not the only type we'll see, and so I'll introduce you to a few of the others as well. But let's start by looking at some ceramic capacitors. Now, these capacitors are very small. If I stick my finger in there, you can get an idea how small they are. This one has a 1/10 inch spacing between the leads. These have 2/10 of an inch spacing between the leads, so they're easy to plug into breadboards. Now, by the standards of modern electronics, these capacitors are huge physically, because modern chip capacitors may be only a few millimeters on a side. But those are too difficult to work with on a breadboard, so these are handy for using on breadboards. They're also extremely cheap, though not as cheap as chip capacitors. Okay, what do we have marked on the capacitor? What can we tell about the capacitor? Generally, the thing we're most interested in is how much capacitance does the capacitor have. And because these things are so small, there isn't a lot of room for putting a lot of text on it. So there's a standard convention that's used for marking capacitors, and that is to put 3 digits on the capacitor. You can see this one's got a 106, hard to see, but this next one has got a 103, and this final one here, really hard to see, it's only got 2 digits, a 68. How do we interpret these numbers? This is not 106 somethings. This is not 103 somethings. No. The first 2 digits are interpreted as a number, and the third digit is interpreted as a power of 10. So this is 10 times 10 to the 6th. This is 10 times 10 to the 3rd, and this is just 68 with no power of 10. You will sometimes see these printed as 680, and that means the same thing as just saying 68. So a 0 means 10 to the 0th, which is 1, and that is often omitted. Okay, so if you have fewer than 3 digits, it's just a number. If you have 3 digits, the last one is to be interpreted as what power of 10 to multiply by. But what are the units? The units for these markings on capacitors are picofarads. So this is 10 times 10 to the 6th picofarads. Well, 10 to the 6th times picofarads is microfarads, so this is 10 microfarads. Similarly, 10 times 10 to the 3rd picofarads is 10 nanofarads. And finally, this 68 is just 68 picofarads. So all these can be interpreted just by looking at the 3 digits and saying that's in picofarads. But the first 2 digits are a number, and the last one is an exponent. And I put a little table in the book to make this a little bit easier to interpret. These are the values of components, the capacitors that we had in the lab kit one year. Every year we end up getting a different cheap assortment of capacitors, and so we end up with different values. But we have here a range from 1 picofarad up to 10 microfarads. 10 microfarads is fairly large for a ceramic capacitor. So you're going to have a hard time finding ceramic capacitors, cheap ceramic capacitors anyway, that are much bigger than that. And we'll use the values in this course. We probably won't end up using the really tiny ones because those really are quite small. The capacitance that we have just from having parallel rows on the breadboard, you've got 2 rows of connectors there, separated by plastic or air insulation. It's a capacitor, and it's going to add 5 or so picofarads to your capacitance. So adding 1 picofarad isn't going to do much of anything. So we're not going to use the tiniest capacitors much, but just about all the ones above that have potential for being used in this course. Now, I have another part on this table here that shows some more markings. And the capacitors we were looking at here, the ceramic ones, didn't have these additional markings. So I'm going to show you a slightly different type of capacitor, which does have some additional markings. And that is probably a film capacitor. I got it surplus, so I'm not really sure exactly what sort of capacitor it is, but it tells me some things about it, like the 564J. The 564 tells me it's 56 times 10 to the 4th picofarads, which would be 560 nanofarads. So 560 nanofarad capacitor. And the J tells me its tolerance is plus or minus 5%. Now, plus or minus 5% is actually pretty good for a capacitor. I mean, you can get capacitors that are more precise than that, but the cheap ones, the cheap ceramic ones, are never that precise. So that's what tells me this is probably not a ceramic capacitor. It's probably a film capacitor, having some sort of plastic film inside as the insulator instead of ceramic. What's the difference? Well, the ceramic capacitors can be very much smaller because the ceramic can be made with a huge dielectric constant in the thousands. The film capacitors use a plastic, and those are like dielectric constants of 2, 2.5. So you're limited to how thin you can make the plastic based on how much voltage you want to put across it. So you usually need a very large area. This capacitor probably has many sort of interleaving plates with plastic between them in order to get sufficient area to get that sort of capacitance. Whereas these ceramic ones can be just 2 plates with a little bit of the ceramic between them as the insulator. Now, the ceramic insulator has some disadvantages as well. It's harder to control to get a precise value. It's temperature sensitive. It's also somewhat voltage sensitive, so that the capacitance isn't really the constant you would like it to be with a ceramic capacitor. The advantage for ceramic capacitors is that they're very, very cheap and very, very small. So they get used a lot when you don't need to be super precise about the capacitance. Now, I said that about the biggest capacitance we could get with a ceramic capacitor was around 10 microfarads. Once you try and go above that, they start getting expensive. Film capacitors, maybe 100 nanofarads. What do you do though when you need something big? When you need to store a lot of charge, which you might, for instance, for power supply. Well, then we use a different sort of capacitor, something called an electrolytic capacitor. Now, the electrolytic capacitors work on a rather different way of creating the insulator. Rather than having a separate material for the insulator, like the ceramic or the plastic that's sandwiched between 2 metal plates, what electrolytic capacitors do is to have the metal plates and to grow on one of the metal plates a very, very thin layer of oxide. The oxide's an insulator. The metal plate is usually aluminum, sometimes tantalum if you've got a lot of money. So usually it's an aluminum plate with a very thin layer of aluminum oxide on it. The aluminum plate, in fact, is roughened so that it has a very large surface area. The aluminum oxide makes a very thin layer over that large surface area. So you have a very thin layer of a very large area, which allows you to get a large capacitance, even though the material itself is not that high a dielectric constant. The aluminum oxide is not much higher than plastics. So it's not like the ceramic where you made the thing get its capacitance by having a very high dielectric constant. Here you go for a very, very thin layer. And that allows here, this one, which is a fairly cheap one, is 470 microfarads. So 47 times that 10 microfarad capacitor in the ceramics. But you notice there's a weird marking here on one of these wires, the minus sign. That's because this is what's called a polarized capacitor. You can only put positive charge on one side, negative charge on the other. If you hook it up backwards, what happens is that that thin layer of oxide, which is next to a wet electrolyte, that thin layer of oxide gets removed from the wire, gets removed from the plate and dissolved in the electrolyte. Once you get to the point where you have direct contact between the electrolyte and the plate, then you can get direct current flow. You no longer have an insulator. And what happens is you suddenly get a very large current. The wet electrolyte gets heated up by this large current, and you get a steam explosion. In fact, the top of this thing, it's out of focus. There. You can see there's sort of a little cross stamped in the top there. Those are burst relief, so that if this thing overheats, it'll pop at that point rather than exploding and splattering the caustic electrolyte all over your electronics. So if you hook up an electrolytic capacitor backwards, it can explode. And we used to use these in the lab in order to get large capacitances, because for quite a while the 10 microfarad capacitors were a little hard to get in the assortments we were looking at. And nearly every year somebody would hook it up backwards and blow it up. Luckily they're not too dangerous, but if you are working with electrolytic capacitors, wear safety glasses. You do not want to get the end of one of these things embedded in your eye. Not only is mechanical damage dangerous, but the electrolyte itself is very caustic, and it'll do a number on your eye if you get any in it. So this one says 16 volts. If you put too much voltage on this thing, it can also blow up. So stick with the 16 volts absolute limit, and make sure that the negative end is always more negative than the positive end. Because of these limitations on the electrolytic capacitors, and because we don't really need storage of large amounts of energy for our labs, we've stopped using the electrolytes in this course and basically just use ceramic capacitors. They're safer, cheaper, and we don't have to worry about polarization. Put them in either way around, they work the same. Okay, that's probably enough for now on the physical capacitors. We'll do another video talking about the impedance of the capacitors.